All right. Well, thanks so much, John, for that introduction. And thanks everyone for being here today. I'm excited to get to talk about a part of my dissertation on some inferential methods for the partial correlations of multivariate Gaussian time series data. Kind of a mouthful, but that's as condensed down as we could get that for the title. So we're going to start with an introduction to the problem we were addressing, what motivated this development of these inferential methods. We'll talk about the inferential methods that we developed and proposed for analyzing this time series data, and then briefly look at some simulations that we conducted to assess the performance of our methods, comparing to other competing methods, and looking at the results overall. So feel free to save your questions for the end. I think we'll have a period for questions at the end, but you're really welcome to ask them if you want to during the presentation as well. So to start with some motivation, what were we addressing here? So if you look at this plot here, this shows a trend in the percent of US adults with some form of mental illness within the past year across time. So what we can see is that for most of the subgroups here, most of the age groups, we have an increasing trend in terms of the percentage of people experiencing some form of mental illness. In particular, you can see among the younger age groups, like 18 to 25 and 18 plus, okay, we have a real increasing trend to where, yeah, those 18 to 25 as of 2019, it was almost 30% of people experienced some form of mental illness in the past year. And if you look at even some of the more recent data, this trend has continued, where it's continued to increase, right? Many Americans are experiencing some form of mental illness. In particular, over 50 million Americans as of 2020 experiencing something like schizophrenia, bipolar disorder, or even just major depression or anxiety. Okay, so a large impact on a large number of people in the United States, and an increasing problem every year. So improved treatments for these mental illnesses is increasingly in demand today, right? And because it's involved with the brain, these diseases, illnesses are directly linked to the brain. Improved understanding of the mechanisms in the brain are essential for helping guide clinicians in developing better treatments. So one way we can better describe what's going on in the brain is to look at what's called functional MRI data, so magnetic resonance imaging data. Most people are more common or more familiar with the more common just regular MRI, magnetic resonance imaging data, where you can get a snapshot of what's going on inside your body, right? So that's what we'd call like a structural MRI, where maybe you have a bad knee or something, and they want to take a picture, take a look at what's going on in there, and it's just a snapshot in time. We also have what we call functional MRI data, where we get repeated snapshots of what's going on inside the brain, typically focusing on the brain across time here. Okay, so what we end up with is this three-dimensional data at each time point. Okay, and at each of these boxes, which we call voxels in fMRI analysis, we get a measure of the amount of brain activity occurring at that snapshot in time. Okay. And so we end up with a signal that's a surrogate measure for brain activity at each of these voxels in three-dimensional space within your brain across time. Okay. These data with these voxels yield this type of study yields very high dimensional data. So commonly we have tens of thousands or even hundreds of thousands of voxels at each time point. And then we're measuring those potentially at hundreds of time points, okay, for a single study. So we as statisticians know that makes our lives a little bit more challenging. Hundreds of thousands of variables with just hundreds of measurements or observations, is what we'd call high-dimensional data. So a lot of traditional statistical methods of inference aren't readily applicable to this type of scenario, at least easily. So one approach to make the data easier to work with and to increase our signal-to-noise ratio is to do what we call dimension reduction. Okay, so instead of just hundreds of thousands of voxels and analyzing that data, we may average the signal from sets of voxels to condense this down into what we call regions of interest. And so these brain regions might consist of contiguous voxels, voxels that are touching each other in space. But sometimes the brain is a very symmetric part of our body, but there's also some parts that are asymmetric in other regards as well. So it is not necessarily contiguous or touching parts of the brain, but some parts of the brain are integrally tied with each other. So some of these brain regions can be in different parts, but they vary exactly with each other nearly. Okay. But the gist of it is we get this dimension reduction. So here, for example, is one, what we call a brain atlas was used to average signals within these contiguous, fairly contiguous regions of the brain, okay, for dimension reduction. So it might be like the parietal lobe or the occipital lobe, and we average just the voxels within those regions. Okay. There's lots of methods for how do we define those regions and different approaches for that, but we just use a predefined mapping for deciding what's in each brain region. Okay. But it's another interesting problem in fMRI analysis is how to define these brain regions. Once we have those brain regions, then we can look at the signal that we have across time. Okay. So for example, this is data on 4 different brain regions within the parietal lobe from a study that I got to analyze data from for part of my dissertation. This was a single participant who was diagnosed with chronic episode schizophrenia. And this is the brain signal, the bold signal, from these 4 subregions of the parietal lobe. Okay. So what we have here on the y-axis is what we call the bold signal. This is what fMRI comes as, which is the blood oxygenation level dependent signal. Essentially, fMRI uses magnets to take advantage of the varying magnetic properties of oxygenated blood, so blood that has oxygen in it more so, and deoxygenated blood to describe where activity is happening in the brain. The idea is that when neurons fire in the brain, they need to have oxygenated blood flow to that to help the neuron fire. So we can use that amount of like oxygenated versus deoxygenated blood as a surrogate measure for brain activity. Okay, that's how fMRI effectively works. Here what we can see is that the green and red region, for example, okay, B and C, are co-activating with each other quite a bit. As green goes down in its brain signal, so does red. And as it goes up, so does the other typically. But there is some noise there. And we can see even though D, for example, has a relatively weaker signal, it's still tending to go down and up, co-varying with the green and red regions here. Okay. Whereas region A, for example, is maybe not co-varying as much. Okay, there's not as much of a strong signal there. Okay. So this idea of looking at the co-varying patterns or how much these brain regions co-vary with each other in terms of their brain signal is one area of fMRI analysis called functional connectivity analysis. And this is what my dissertation was all about, methods within this realm of functional connectivity analysis of fMRI data. So formally, this is defined as the temporal dependence, okay, so relatedness across time of brain activity levels in different regions of the brain. So this is important to look at because alterations in this functional connectivity, how these brain regions covary with each other in terms of their signal, can be associated with certain psychiatric disorders and neurodegenerative diseases. So for example, it may be that in a healthy control, these brain regions go up and down with each other in a nice cohesive fashion, but maybe for someone with, for example, chronic episode schizophrenia, it could be the case that there's some type of disruption so that there's a little bit more disconnect between those two brain regions, so they're not covarying as much. And if that's the case, then we know that maybe something's going on in those two brain regions, so that can help inform a clinician about, okay, maybe we have like a drug or some other type of treatment that targets those areas that we can then see if that helps with the chronic episode schizophrenia. Okay. So how do you describe how related those two signals are across time? Well, again, as statisticians, we know there's lots of options on the table, right? So one of the more conventional choices is just Pearson's correlation coefficient, the marginal correlation. That describes the linear dependence between those two signals. We can also look at what's called the partial correlation coefficient. So this is the relationship between two signals after removing or regressing out the effect of the other brain regions. Okay. Other commonly used measures are coherence, which describes dependence on the frequency domain. For time series analysis, we have the time domain, which is what we traditionally work in as statisticians. And then there's also a representation of time series data in the frequency domain. So you can describe dependencies in that domain as well, and that's coherence. We also have what's called mutual information, which the basic idea behind that is you can look at the marginal distributions of each variable and then the joint distribution together and see the difference between just the product of the marginals and the joint. And the amount of difference between those two describes mutual information. Okay. So lots of options here for describing functional connectivity. Again, for my dissertation, we focused solely on the partial correlation coefficient. Okay. And so with a measure like the partial correlation coefficient, which is depicted here for that same graph, okay, we can construct what we call a graphical model of the data, where we have nodes representing regions of the brain and non-zero correlations between those nodes, okay, representing connections in the network. Okay. So for example, here we have regions A and B have a connection because their partial correlation is 0.17, and A and C are connected as well, but D was not connected to regions A and B, okay, just to see.
Zero ones, are they specified to be zero or strained to be zero?
Exactly. There was some type of lasso penalization to shrink these to be exactly zero. Yep. Yeah, because if you look at the raw values, of course, the chance of getting exactly zero, nearly impossible. Right, so yeah, typically some lasso shrinkage is done here. And so the idea is that, again, maybe this can help us visualize, say, with a healthy control, maybe this is how the network looks. But with someone, say, with chronic episode schizophrenia, maybe there's several edges that are missing connecting D to other areas. And that might help, elucidate the fact that, oh, that brain region, something's going on there. Maybe there's a targeted treatment we can come up with. So I mentioned how there's several choices for the dependency measure that we can use, partial correlation being one of them. Marginal correlation is likely the most widely used, but partial correlations have some benefits. So they describe the relationship after removing the effect of other variables. So some assert this more closely is related to what we call effective connectivity, the influence that brain regions have on one another. So it's slightly more getting at a causal relationship potentially, but we know, of course, even the partial correlation does not necessarily prove causality, but the idea is that it gets at it more closely than just the marginal correlation. So it might better describe these co-varying activities that are going on in the brain signals. So how can we define this partial correlation coefficient? There's several ways you can view the definition of the partial correlation coefficient. What will be convenient for our problem here is viewing it as a function of the residuals, okay? So if we have a time series with n time points, okay, so you can imagine n snapshots of the brain across time with p variables, okay, we'll call this a p-variate Gaussian process that's second order stationary and ergodic. Okay, essentially, we're assuming it has a constant mean and covariance structure across time. That's what second order stationary is referring to. And then ergodic is just a nice property about time series data such that if we have a longer and longer time series, we're going to be able to better estimate parameters necessary for the model. The idea is that, you know, if we had a long enough time series, we should be able to have very good estimates. It shouldn't be behaving badly as it goes off into space, okay? So very reasonable assumptions for, say, fMRI data. For resting state fMRI data in particular, where people are just sitting at rest, not doing any type of task, which is what we'll be focusing on here. And so given this data, one way to view the partial correlation coefficient is the function of the residual shown here, where we have for a variable xi, we can calculate an n-length vector of ordinary least squares residuals, where this is the set of residuals from regressing xi on all the other x's except xj. We do the same for xj. We regress xj on all the other variables except xi, get its own set of residuals. So essentially what's left unexplained by all the other x's besides xi and xj, we then look at the correlation or marginal correlation between these resulting ordinary least squares residuals. Okay, that gives us what we call the partial correlation coefficient. And you'll notice here, again, we're conveniently representing this as a function of this stacked vector of the ordinary least squares residuals, where we have the inner product in the numerator and the square root of the products of the inner products down below. So that will be important. Keep that, tuck that away for now. Hey, the partial correlation is just a function of the residuals. Now, we can calculate the partial correlations fairly easily for time series data, and that gives us our graphical model. But it's important that we're able to describe the amount of uncertainty in those partial correlations. Okay. So how can we do that? Well, we can use standard errors and confidence intervals, but a lot of the methods for partial correlations, derived standard errors and confidence intervals, rely on an assumption of independent observations or normal data, okay, which is not reasonable for fMRI data. So for example, from Kramer, we have this standard error for the partial correlation between variables xi and xj. But yeah, as I mentioned, not reasonable for fMRI data. There's strong temporal dependencies here. So for example, if the signal at time 125 here for the green region is up here, the signal at time 126 is going to be quite similar. Okay, so it's kind of sticky in a way. It doesn't just randomly fluctuate through the whole space. There's some stickiness as we go left to right in the plot. And that temporal dependence violates many of the assumptions for traditional standard error derivations or confidence intervals for the partial correlation. So here's our problem. We want to use the partial correlations to describe functional connectivity, but we also want to be able to describe uncertainty in those partial correlation estimates for time series data, okay, that properly accounts for this temporal dependence in the data. And this was the main task in the second chapter of my dissertation. To be honest, there's many methods out there, many publications in fMRI data that just ignore the fact that it's time series data, right? And use conventional methods. It sounds like, ooh, that's not good. And yes, that's true. It's not great because it's not the easiest aspect to address about the data, right? So that's what we tried to do here. And so after not many days, not even many weeks, after months of working on this problem, one approach I came up with was to derive the joint distribution of the partial correlations that we can calculate for multivariate time series data. Okay, just with some mild regularity conditions. Okay, that second order stationary assumption, an ergodic time series. And this joint distribution, which also gave us an avenue for describing the variance or standard errors of these partial correlations, allows us to then use or implement some inferential methods for the partial correlations. So we can do walled tests, like a z-test, or make a confidence interval for these partial correlations now using this joint distribution that directly accounts for this time series aspect of the data. Okay. Now, how did we derive this joint distribution? This was already done, Hedges and Olkin derived the distribution for the partial correlations for independent observations and normal data, but this had not been done for a general multivariate time series yet. Okay, so let's revisit back again how the partial correlation can be represented as a function of our ordinary least squares residuals. Okay, so we're going to remember that, and then also look at our friend Taylor here. So not Taylor Swift, but another important Taylor, the Taylor series of a function. Okay, so we have the Taylor series for a univariate function, as a brief reminder, can allow us to approximate or represent a function via this weighted sum of derivatives of the function with this expansion about a point A. So if we have a function f of x, this is equal to, okay, from Taylor's theorem, f of a plus the first derivative of f evaluated at a, okay, with this infinite summation of many terms. This is helpful in math, as we know, because if we have a function that's maybe difficult to work with, f of x, sometimes the Taylor series representation of that function can be a little bit easier to work with. Okay. So visually, what's going on with the univariate Taylor series here? If we have a truncated Taylor series, so if we just use the first, say, 1 or 2 terms, we can approximate a function and sometimes do that fairly well if we're just concerned with a certain range of values here. So for example, here's a first order Taylor series approximation of the function sine of x, which is just a straight line. Okay. And this was an expansion about the point 0, so sometimes just called the Maclaurin series. If we went out to that second term, okay, if we include the second derivative term out here, we then get a little bit wigglier of line, and it approximates the function a little bit better, right? A little bit further out from that expansion point. And then a third order approximation. Okay, we even get the line doing very well, even if we get somewhat further away from 0. Okay, so the idea is that this function might be much easier to work with f of x, and it still might give us a very close answer to what we get with using that same original function for our data. So in statistics, we can take advantage of this Taylor series in a number of ways. So many results in statistics are based on Taylor series. I think it was my friend Veronica Burt said, everything is Taylor series if you view it from a certain angle. So one way we can use Taylor series in statistics is to approximate the moments of a function of a random variable. So for example, if we have f of x, where x is just a univariate random variable, we can get this approximation of the expected value of f of x. Okay, the idea is maybe we know the moments of x, okay, like the first moment and the variance of x, but maybe the first moment of f of x is difficult to derive analytically, so we could use this Taylor series approximation of the expected value of f of x. And it's not perfect because we're not using every term in the Taylor series here, but the idea is those terms get closer and closer to zero typically as you go out. And so this can often give a pretty good approximation of that expectation. Okay, and then we can do the same thing for the second moment of f of x, which then could allow us collectively to estimate, say, the variance of f of x. Okay, and if we remember back, oh, we wanted to estimate the variance of the partial correlation, which was a function of our data. Okay, so we're going to kind of take advantage of this approach here. So for those who've taken maybe some graduate level math stat classes, you might be thinking, oh, this kind of looks like the delta method, right? So the delta method is integrally tied to this idea of using Taylor series to approximate moments. Right? Now, we had the case that the residuals were a vector. Our function f to represent the partial correlation was a function of the residual vector. So we actually are working with a multivariate function here, where it's f of x and x is a vector input that's mapping to a scalar output. Okay. We can have a multivariate Taylor series expansion as well, right? So we have f of a, where a is a vector that we're doing the expansion about here. And then we have a term with the gradient of f, which is a multivariate version of the first derivative. And then we have the Hessian matrix, which is a matrix of second order partial derivatives, okay, analogous to the second derivative in the univariate case. So similar to the univariate case, we can again use a multivariate Taylor series with the truncation of the Taylor series to get approximate moments of multivariate scalar valued functions. Okay, so if f of x maps to a single number, we can approximate the expected value of f of x if we know the moments of x. And similarly, we can get an approximation for the variance of f of x. Okay. So this is the approach we're going to be using here to estimate the variance of the partial correlations. Okay. The expected value, if we have a consistent estimator for the partial correlations, I mean, it's great if this ends up being partial correlation, the true population partial correlation, but this is what we were after here, is the variance of f of x, where f of x is going to be representing the partial correlations that we're interested in. Okay. And so here's how we did that. So we said, hey, let's view the partial correlation coefficient as a function of the residuals here. And we're going to do a second order Taylor series expansion. Okay, so using out to two terms through the Hessian matrix here of this function of the ordinary least squares residuals. Okay. And now, as we looked at before with the Taylor series expansion, we can do this about a certain point, a particular point, and we get to choose that. But we want to be careful about how we choose where we're doing the expansion, right? So here, what we're doing is we decided what would work the best is to pick this point epsilon ij, such that f of epsilon ij is equal to the true population partial correlation between variables I and j. So note that we don't know epsilon ij. We don't get to see that for real data. We're just saying, hey, suppose we did know what that point was, and that's what we're doing the expansion about, right? We're kind of pretending it won't be a problem, and we're going to worry about it later. We're just going to get the expansion now. Okay. So we get our second order Taylor series expansion. Okay. And so we end up with this term here. Okay. Now, instead of estimating just the variance of the partial correlation, we can try to just figure out what the variance of this term is. Which, to be honest, when I got to that point, it was like, oh, is that actually easier? Or if we just found a more difficult problem now. Okay, but we were able to figure that out. Okay, so fortunately, what I recognized is when you simplified things down here, this looked a lot like what we call a quadratic form, okay, in statistics, multivariate statistics. And there's lots of nice known properties about quadratic forms, in particular, what the variance is. That's already been figured out, right? So based on properties of quadratic forms, using this multivariate Taylor series expansion, this gamma tilde ij gives us the asymptotic variance. Okay, asymptotic because we're only using a second order Taylor series approximation, not the full Taylor series. This gives us this asymptotic variance form of the partial correlations. Okay. And actually, not only did it give us the variance of a single partial correlation, but if we had a function where you stacked four residual vectors for two partial correlations like Rij and Rkm, using properties of quadratic forms, you could also get the covariance between two empirical partial correlations. And that's how we were able to get the joint distribution of a set of all the partial correlations that you get from multivariate time series data. Okay. And what we end up with in here is this covariance matrix that's very big. Okay, so n is the length of our time series. We end up with this sigma ij, where we have the covariance of this residual vector, other residual vector, okay, which is not great on the surface because we have n time points. And if we want to estimate this covariance matrix, it's a 2n by 2n matrix. We have a very large number of parameters to estimate now, okay? Not good when the number of parameters we're estimating is much larger than our sample size, right? But that's where our assumption of the time series having a constant covariance structure across time is going to help us out here, okay? We can use what are called tapered covariance estimators that essentially assume rely on this assumption of the covariance between 2 points only being a function of the lag between them, the distance between them in time. Okay, so for example, we assume that the covariance between the value of x1 at time 5 and x1 at time 8, that covariance is going to be the same 3 time units apart as the covariance of x1 at time 10 and x1 at time 13. Okay, so in that way, we can have a more stable and reliable estimator for the covariance matrix. Okay, and so this was something that was already solved by somebody else for time series data. How can we estimate the covariance matrix when it's you end up with more parameters than the length of the time series, right? This is one approach for doing that, using what's called a tapered covariance estimator. Okay, and it's tapered because essentially you assume the covariance goes to 0 if you get far enough apart in time at some point. Okay. So that's how we estimated the sigma hat ij. How we estimated the Hessian matrices is we just used method of moment estimators, okay, which is kind of a fancy way of saying I just plugged in the residuals for those theoretical epsilons. And that tended to work well. So now that we have our asymptotic variance here, we can use this variance as a standard to get our standard errors, to construct confidence intervals, to do Wald tests, all kinds of things that we want to do with those partial correlations. Just doing a standard Wald confidence interval here with a z star multiplier. So having all this theory is one thing. Does it actually work for time series data though? So yes, for here we did a simulation simulating 1,000 data sets from this vector autoregressive model, which is a common time series model that's used to simulate fMRI data. So we consider a time series of either length 100 or 500, varying numbers of variables, 5, 10, and 15, and then varying amounts of autocorrelation defined by this autocorrelation parameter, phi. And so phi of 0 corresponds to independent observations, which is what many of the conventional methods assume, whereas a phi of 0.4 and a phi of 0.8 correspond to more autocorrelation being present in the data. So a stickier time series, the larger the value of phi, the stickier the time series is in time. For many of the data sets I analyzed for fMRI data, an autocorrelation parameter of 0.4 is ballpark reasonable. Okay, so right in the middle here. And then we generated these partial correlations uniformly from the set, minus 0.3, 0, and 0.3. So maybe sometimes in class we see correlations of like 0.8 or 0.9, but realistically for fMRI data, the signals are often very weak. Like the connections are there. You can see it consistently across people, but it's not the strongest correlation always. Okay, so this was realistic based on the fMRI data we observe. So what do we compare to? We compared to this conventional confidence interval that assumes independent observations. Okay, so here's how we can construct a confidence interval for that using a t-star multiplier and that proposed standard error. So we expect this to do well in the independence case, but not as well when there's time series, when there's autocorrelation present in the data. Okay. Another common thing that's done for correlations when constructing confidence intervals or conducting inference is to use what's called a Fisher transformation, also known as the inverse hyperbolic tangent of the partial correlations. Okay, so essentially it's 1/2 times log of 1 plus r over 1 minus r. Okay, this is what we call a variance stabilizing transformation of the correlations. For normal independent data, this has been shown to make the standard error of the correlations a function of the sample size and number of variables instead of the correlations themselves. Okay, so often when people say are conducting inference of the marginal correlations for fMRI data, they might do a Fisher transformation in their analysis for variance stabilization. Okay, so we wanted to compare it to that approach as well. And then lastly, some papers do that. Some people just compare to the methods that assume independent observations. I felt like it wasn't really a fair comparison. If we're going to look at time series data, of course we'll win if it's comparing to assumptions that rely on independent observations. Like, it felt like the simulation's not even necessary to do that, right? So I tried to come up with an approach that accounted for the time series data, but of course that wouldn't require deriving a whole new method or something like that, a whole nother paper, right? And so one approach for estimating uncertainty in statistics that we're interested in is the bootstrap, right? So a very nice flexible method, but the conventional bootstrap relies on an assumption of independent observations as well. Okay, but one of my advisors, Mark Fiekis, was familiar. He's very familiar with time series data. There's time series flavors of the bootstrap. Okay, so we can make minimal assumptions about the data, but still get these non-parametric estimates of standard errors and confidence intervals. So the block bootstrap is one time series flavor of the bootstrap that only relies on an assumption of a stationary time series, which we needed for our own method as well. Okay, and then we can use that to calculate confidence intervals as well. Okay, and so to be honest, I was a little bit nervous because it's like, oh, you come up with this good competing method. Is it just going to beat what we had? But I felt like we gotta be honest about how we're doing it, right? Yeah, just we forgot about that one, right? And so this was already proposed, early 2000s. Oop. Oh no, that took us way away. Okay, this was already proposed early 2000s, and so we implemented this, had to code it up in R, which took a considerable amount of time. But once we got that working, okay, we compared that. And so a visualization of what's going on with the block bootstrap here. the idea is that instead of resampling individual observations for the block bootstrap, you resample contiguous blocks of the data to preserve the temporal dependence of those observations. So you resample blocks with replacement, use those to reconstruct your time series, okay? And then you still have some temporal dependence because of the window size, okay? And then we can reconstruct many bootstrap samples in that way, calculate the partial correlation for these, say, 5,000 times, and we can get a bootstrap distribution of partial correlations. And so how big this window size needs to be, you can make that a data-driven approach, right? So there's methods proposed out there for, based on how sticky the time series tends to be, we might need to make the window bigger or smaller, more narrow. And so we just did that in that data-driven way. Yes, and that's how we implemented the block bootstrap. And technically we implemented what's called the circular block bootstrap, such that if a window happened to fall in the end and some of it would be falling off there, you just act like you kept going at the beginning, like it circles back around to itself. That's the name circular. Okay.
Andrew, quick question. So
Yeah.
the goal on the size of the block was to make it, am I correct, that the first and last observation are independent of them?
Right, or very close to
Close.
it. Exactly. Yep. Yeah. Yeah.
Did that help you decide when the beginning of the box started and when the end of the box ended?
Exactly. Like the window length is a thing we estimate or decide based on the data. So given the window length, we then just pick a random starting point and put the window.
It's just random.
Yep.
Okay, so piggybacking on that, how on earth is the one in the middle not having disjointed things between, like they connect, so one connects with two?
Right.
That's not luck, right?
No, not luck. It's effectively like instead of drawing the individual points, I drew a line chart that has lines just connecting the adjacent points here in the segment. So it's making the line is making it seem more connected than it is, but you're right, there's disjoint. Yep. And so we compared all those methods, constructed 95% confidence intervals. And so here's how our results look. So we have each column here is representing different amounts of autocorrelation present in the data, the first column being the independence case. So this is where we would expect the competing methods to do well. Theoretically, I mean, they should beat our method. It's perfectly matching the assumptions that they rely on. And we see that that's the case. The Fisher and naive approaches, which rely on an assumption of independent observations, okay, have pretty much in the 5-variable case. So we have 5 variables in the top row and 15 variables in the bottom row. In the 5-variable case, they have pretty much exactly 95% coverage. But you'll notice that our method, the Taylor method in green, and the block bootstrap, also very close to 95%. So what's great is our method adaptively, it adapts to the amount of autocorrelation in the data. So even in the independence case, it works similar to the traditional methods. But as more autocorrelation is present, you can see the drop in the performance of the competing methods, which rely on an assumption of independent observations. Effectively, they are too confident. They think they have more information than they actually have, because in time series data, you can think of it as that there's some redundancy in that information. If we have 200 data points, but they're kind of sticky, your effective sample size is not really 200, it's somewhat less. And so that's what our method is accounting for. Yeah.
I wasn't paying attention when you covered all those different methods, but is your method a generalization of the Fisher or naive approaches, such that if you plug a 0 in with a correlation, it just almost algebraically or mathematically, ends up being the same equivalent thing, and yours is just more general, or no?
Nearly. That was something I tried to show for the paper, and it was very close, but there's some, essentially asymptotically, yes, there's some terms that will go to a 1 or a 0, but it does, yes, if you plugged in 0 for, let's say, the autocorrelation estimates, it becomes nearly the same as the other. Yeah.
I'm kind of confused on what makes it multivariate in that when you started and talked about the four regions and A, B, C, and D,
Mhm.
I thought that's what was defining it being multiple time series.
Right.
But here, aren't we just talking about blocks within a single time series?
Yes.
And are the blocks
Mhm.
defining what's multivariate or what am I missing?
Right. Yeah. So you're right that this is univariate results. These are univariate confidence intervals. Exactly. The multivariate result is the fact that we derived the joint distribution for the whole set of partial correlations. So essentially, we ended up with that they're asymptotically multivariate normal, derived the covariance matrix for the partial correlations. But here we're just looking at univariate confidence intervals for each one at a time. Yep. And you'll notice that in the 15 variable case, the performance of all the methods suffers, which I thought maybe something was going wrong here at first, but upon further inspection, essentially what's happening is if you have a larger number of variables with the partial correlation, you're estimating p choose 2 parameters. So what I noticed is the estimates of the partial correlations themselves, what the confidence intervals were centered on, was quite poor as p got larger, and that affects all the methods. So that's why the coverage gets poor. So big thank you to my advisors, Lin Zhang and Mark Fiekas, who were incredibly helpful on this project. I could, without their encouragement, I don't think I would have had the courage to try this. Lin in particular, very positive and supportive. I feel like she was very good at coming up with ideas for like, this would be a good paper. You can get this done in a year. But I was like, I want to try this. It's maybe a little more challenging. Is that okay? I was very thankful. She was very supportive of that. Like, even though it was something newer, maybe a little bit more out there, she was always supportive. And then, like I said, Mark's time series experience was so helpful with like the block bootstrap suggestion. And all of this had to be coded up in C++ because it was so high dimensional and slow running. And Mark was incredibly helpful with the C++ to help it run faster. And yeah, so this was published in Biometrica last year with supplementary material and an art package that I made available on my website for those who are curious. Yeah, so thank you all for coming today. And I'll stop the recording here, and then we have a little bit of time for questions, maybe.
Yeah, we have about 10 minutes, and as the host of the seminar series, I'm the host